inertia using the tools of calculus. This object is a solid sphere. It has a uniform density. It's solid, it's not hollow. Uniform density with a radius capital R. The sphere is rotating, and we're interested in knowing its rotational inertia, or its moment of inertia. And we want to do this, come up with an expression that's a function of the mass and the radius of the sphere. So I'll review a little bit here, and starting with the picture over on the left, we have a sphere. Our situation is that we need to add up all the contributions of some infinitesimal mass times r squared as our basic expression for the rotational inertia. If I have a point mass m at some distance r from the axis of rotation, its rotational inertia is mr squared. So we're going to find the infinitesimal masses here, each at a distance of r that's squared, and add all those up using the antiderivative. Well, we can accomplish this if we would think of a disk through here. So a horizontal slice through this, I don't know if I'll mess up the drawing too much here, but going on back behind. So think of a disk, a short cylinder, and I've shaded in an edge along the front of the sphere that we can see here. And we're going to find an expression for the mass of this disk. The mass of this disk. Well, to accomplish this, let's think about density. It's mass over volume. For the disk, the volume is the area, pi r squared, multiplied by dx, the thickness, the vertical up and down thickness of the disk. If I rearrange this, first over here, this mass would be density times volume. We want an infinitesimal mass. That's going to be accomplished by this infinitesimal volume that's created by the dx, a very small number, dx. So the density, that's the symbol rho, times the volume of the disk, gives us the mass of the disk, the dm. We're going to need a substitution here. So think about a right triangle. If here's the center of the sphere, and up here is the center of the disk, we have a right angle. So this distance x is from the center of the sphere up to the center of the disk, and then r, the radius of the disk, comes out here. It's a right triangle, so x squared plus r squared would be capital R squared, the radius of the sphere. And solving r squared is capital R squared minus x squared. So I'm going to substitute that in. And we now have pi, rho pi, the quantity capital R squared minus x squared dx. I want to do this. R is a variable, as we're going to take the antiderivative from the bottom to the top of the sphere, and R changes. So I want to use x as my variable of integration. I've got a dx here. So we made a little substitution. This variable r is replaced with an expression that has a variable x in it. So let's go ahead and proceed here with some of the calculus steps. R squared dm. We're doing a disk here. Well, this disk, a disk has a rotational inertia formula of 1/2 mr squared. So I'm going to be using the half from this formula and then doing the r squared dm in the antiderivative. So my dm, I have r squared minus x squared. I have rho pi and another r squared minus x squared and the dx. So how did I get this other r squared minus x squared? I want you to follow along and not just listen to what I'm doing, but be thinking here. Now this last portion here, starting with the rho, this is dm, and we have an r squared here. That r squared is capital R squared minus x squared. So that's where this other factor arises from. We're going to take this antiderivative from x being at the bottom here, minus r, to x along this rotational axis being at the top at plus r. So it's a little tedious, a little messy, but it's not hard. So kind of follow along here with your calculus skills and your algebra skills. Here I'm distributing r squared minus x squared on r squared minus x squared. And I'm pulling out the constant factors, so the rho and the pi come out front. And r squared times r squared, that's r to the fourth. And there are two of these occurrences of r squared times x squared, both of the minus sign. So we get minus 2 r squared x squared, and then minus x squared times minus x squared gives us plus x to the fourth. In doing the antiderivative, we have really x to the 0 on this r to the fourth term. The antiderivative lifts up the power of x by 1, and then we divide by that new power. R to the fourth is a constant, so that is sort of a coefficient. Here we have an x squared. That becomes x cubed over 3. And again, the 2r squared coefficient with the minus sign is survives. And where we have x to the fourth, that becomes x to the fifth divided by 5. I need to evaluate this expression at the upper and lower limits of the antiderivative, so at plus r and at minus r. So let's go ahead and do that. So I have pi, rho pi over 2, and then using the plus r, I'd have r fourth times capital R, that's an r to the fifth, minus 2r squared, and then capital R cubed, that's another r to the fifth, and minus 2/3, and then r to the fifth over 5. Then we subtract when we evaluate at the lower limit. So I have a minus r to put in here in place of x. That produces a minus sign, r to the fourth, and give r to the fifth, a 2/3 r to the fifth, again an odd power, so the minus r and this minus sign combined to be a plus. And here another odd power, so our sign of minus r survives, and we have a minus r to the fifth over 5. Well, we have some like terms here. You can see lots of r to the fifths, so let's see how they combine. Again, the constant out in front, rho pi over 2. I have a minus to distribute through here. That's going to create a plus r to the fifth. With this r to the fifth gives me 2r to the fifth. I have a minus 2/3. This minus sign distributes through here. I get another minus 2/3. So I've got minus 4/3. I have r over 5. The minus sign here creates a positive r to the fifth over 5 again, so I've got two of those. We have denominators here. We've got a 1. We've got a 3. We've got a 5. The lowest common denominator is 15. So to write this first term over 15, I have to multiply and divide by 15. So I get 30 over 15. Similar here, I have to multiply by 5 on top and bottom. So I get 20 over 15. And there's a negative. And here I have to multiply by 3. So I get 6 over 15. Making progress. Combining, I've got 30 minus 20. That would be a 10 for the net there. And then a 6. So I get 16 r to the fifth over 15. We can reduce this a little bit. The 16 divided by 2 gives us an 8. And r to the fifth. Now, I want to get rid of the density and bring in the mass. My formula I want to have in terms of the mass and the radius. So to do this, the density is equal to mass over volume. The mass of the sphere, capital M, 4/3 pi r cubed, that's the volume of the sphere, and then divide by rho. So that would be an equality, really a kind of conversion factor. And we're going to get lots of cancellations here. The rho's are going to cancel, the pi's are going to cancel, r to the fifth and r to the cube partially cancel. We get an r squared, and we're left with I equals 2/5 mr squared, the mass of the sphere and the radius squared of the sphere. And that's our result for the rotational inertia for a solid sphere. Calculus has allowed us to compute this formula. You'll see this in various tables of rotational inertia. And again, the key concept here, rotational inertia for a point mass is mr squared. We have to add up m times r squared. We used a disk. A disk itself is 1/2 mr squared. we have to account for the mass filling into the axis, so we can't use mr squared. This would be mass all the way to the edge, all of it. A disk is filled in. That turns out to create a factor of a half for the rotational inertia formula. Crank through the antiderivative. Again, you might want to pause and inspect all these terms and ask your instructor some questions, but the rotational inertia for a sphere, solid sphere, uniform density, is 2/5 mass of the sphere and r squared.